Have you ever stopped to wonder, not what you are seeing, but that you are seeing at all? You're looking at this screen right now. Light is hitting your retina. Signals are racing down your optic nerve. Patterns are being processed in your visual cortex. We can map every single step of that journey. We can trace the electricity, follow the chemistry, and chart the entire biological process with breathtaking precision. But here's the $5 trillion question. Why does all that mechanical processing feel like something? Why isn't it all just happening in the dark? Why is there an inner movie, a subjective, first-person experience of the color blue, the warmth of the sun, or the sting of regret? This isn't just a tough question. It might be the last truly great mystery of science. And the search for an answer is taking us from the familiar world of our own minds to the absolute bedrock of reality itself, to a place so strange, so counterintuitive, that it forces us to question everything we thought we knew about the universe and our place within it. Let's begin with a simple sensation. The color red. Imagine a ripe strawberry. Your brain, a 3-pound universe of roughly 86 billion neurons, is performing an astonishing feat. Photons with a wavelength of about 650 nanometers bounce off the fruit, enter your pupils, and strike specialized cone cells. This triggers a cascade of electrochemical signals that surge through a labyrinthine network of nerves, ultimately creating a complex pattern of activity in the occipital lobe at the back of your head. We can track this. We can put you in an fMRI machine and watch these areas light up. We can measure the neurotransmitters, the electrical potentials, the entire chain of causation. These are what the philosopher David Chalmers famously called the easy problems of consciousness. I say easy with a bit of irony, of course. They represent monumental scientific achievements. But they are easy in the sense that they are, ultimately, problems of mechanism. They are about how the brain processes information, how it focuses attention, retrieves memories, and controls behavior. But then, we hit a wall so profound, it defines the boundary of our current understanding. This is what Chalmers termed the hard problem. The hard problem doesn't ask how the brain processes the information for red. It asks why that processing is accompanied by the raw, private, ineffable feeling of redness. Why does all that neural machinery generate a subjective experience? Think about it. A self-driving car can detect a red light. Its sensors register the wavelength. Its computer processes the data, and it sends a signal to the brakes. It performs the function perfectly. But no one seriously suggests the car is experiencing the glorious, vibrant sensation of red. It's all just processing. So why aren't we just incredibly sophisticated, biological robots? Why does our complex processing burst into this rich, technicolor internal world? This gap, this chasm between the objective, physical processes of the brain and the subjective, qualitative reality of the mind, is the heart of the mystery. It's the ghost in the machine that science has yet to explain. For centuries, the dominant scientific view has tried its best to ignore this ghost, or rather, to insist that the ghost is just an illusion created by the machine's complexity. This is the classical computational theory of mind. Shaped by the clockwork universe of Newtonian physics and supercharged by the computer revolution, this perspective sees the brain as nothing more than an astonishingly complex biological computer. A machine made of meat, as the saying goes. One of the most brilliant proponents of this view was Francis Crick, the co-discoverer of the DNA double helix. He put it bluntly in what he called his astonishing hypothesis, that our joys and sorrows, our memories and ambitions, our sense of personal identity and free will, are in fact no more than the behavior of a vast assembly of nerve cells and their associated molecules. In this model, the brain is the hardware. It's the wetware, the intricate tangle of neurons and synapses. Consciousness in this view is the software. It's the operating system, the emergent property that arises when the computations become sufficiently complex. Just as a single transistor is dumb, but billions of them working together can run a complex simulation, a single neuron is a simple biological switch, but billions of them firing in concert produce the symphony of the human mind. This framework has been incredibly powerful. It's the foundation of modern neuroscience and artificial intelligence. It has allowed us to understand learning, memory, and decision-making with ever-increasing clarity. But for all its power, the computational theory has a fatal blind spot. It describes the machine's functions with exquisite detail, but it can never bridge that explanatory gap to feeling. You can write a perfect simulation of a weather system on a supercomputer, down to the last molecule of water vapor. It can predict the storm with perfect accuracy, but no one would claim the computer is actually getting wet. The simulation of a feeling is not the feeling itself. The classical view describes how the brain processes the information that leads to you saying, "I am happy," but it offers no fundamental reason why that processing should feel like anything at all. It describes the mechanics of the machine, but it cannot explain why, at some point in its evolution, the machine suddenly woke up and found the lights were on inside. When the familiar, predictable world of classical physics, the world of billiard balls and clockwork planets, fails us so completely, where do we turn? The path inevitably leads to the most bizarre, the most successful, and the most mind-bending theory in the history of science: quantum mechanics. If classical physics describes our everyday reality, quantum mechanics describes the subatomic world from which that reality is built. And that world operates by a completely different set of rules. Quantum mechanics was born from a series of observations in the early 20th century that simply broke the old laws of physics. Light sometimes behaved like a wave and sometimes like a particle. Energy wasn't a smooth, continuous flow. It came in discrete, chunky packets called quanta. This was a world not of certainty, but of probability. It was a world of radical concepts that defy all common sense. One such concept is superposition, the idea that a particle, like an electron, doesn't have a definite location or state until it is measured. Instead, it exists as a wave of potential, occupying all of its possible states simultaneously. Imagine a spinning coin before it lands. It's not heads and it's not tails. In a sense, it's a blurry potential of both at once. That's superposition. Then there is the famous uncertainty principle, which states that there is a fundamental limit to what we can know about a particle. The more precisely you know its position, the less precisely you can know its momentum, and vice versa. It's not a limitation of our instruments, it's a fundamental property of reality itself. And perhaps strangest of all is entanglement, what Einstein famously called spooky action at a distance. Two particles can become linked in such a way that they share the same fate, no matter how far apart they are. If you measure the state of one, you instantly know the state of the other, even if it's on the other side of the galaxy. This granular, probabilistic, and deeply interconnected reality is a universe away from the predictable, deterministic machine of classical thought. It's a world where potential is just as real as actuality, and where the lines between observer and observed begin to blur. Here, we arrive at the pulsating, paradoxical heart of quantum theory, a puzzle so deep it has kept physicists awake at night for a century. It's called the measurement problem. According to the foundational mathematics of the theory, the Schrödinger equation, a quantum system like an electron will evolve smoothly and deterministically over time, its wave of potential spreading out to encompass all possibilities. It remains in this ghostly superposition until a measurement is made. The moment a measurement occurs, something dramatic and unexplained happens. The wave function inexplicably collapses. The cloud of probability vanishes, and the particle snaps into a single, definite state and location. But what is a measurement? This is the question the theory itself refuses to answer. Does it require a conscious human being, a physicist in a lab coat? Or is a simple, automated Geiger counter enough? Or could even a dust particle interacting with the system count as a measurement? The theory is silent. This ambiguity led the brilliant physicist Eugene Wigner to devise a haunting thought experiment called Wigner's Friend. Imagine a scientist, let's call her Frida, who is inside a completely sealed laboratory. In that lab, she performs a quantum measurement on a particle. Let's say the particle is in a superposition of being in state A or state B. Frida measures it and finds it in state A. From her perspective, the wave function has collapsed. The reality is definite. But now, imagine her supervisor, Wigner, standing outside the sealed laboratory. Since he has no information about what happened inside, from his perspective, the entire laboratory, including Frida and her measuring device, is now part of one giant quantum system. Therefore, according to the Schrödinger equation, the entire lab is in a superposition. There's a version of reality where the particle is A, and Frida has seen A, existing simultaneously with another version where the particle is B, and Frida has seen BA. So who is right? Did the collapse happen when Frida looked at the particle? Or does it only happen when Wigner opens the door and asks Frida what she saw? This thought experiment shatters the idea of a single objective reality. It suggests that reality might be relative to the observer. It implies that the observer isn't just a passive witness to the universe, but an active participant who, by the very act of observing, seems to transform potential into actual. The universe, it seems, might hold its breath until someone decides to look. To drive home just how absurd and profound this observer paradox is, physicist Erwin Schrödinger concocted the most famous thought experiment in all of science. It is a macabre little story designed to drag the weirdness of the quantum world up to our familiar, macroscopic level. Imagine, he said, a cat locked inside a steel box. Along with the cat, there is a tiny amount of radioactive material, so small that in the course of 1 hour, there is a perfect 50-50 chance that a single atom will decay. If it does decay, it triggers a Geiger counter, which in turn releases a hammer that smashes a vial of poison, killing the cat. If the atom doesn't decay, the cat remains alive. Now, we seal the box and wait 1 hour. According to a strict interpretation of quantum mechanics, the radioactive atom inside the box is unobserved. Therefore, it is not in a definite state. It hasn't decayed, and it hasn't not decayed. It is in a superposition of both states, decayed and not decayed, simultaneously. But because the cat's fate is directly linked to the atom, the cat itself must also be in a superposition. Until we open the box and make a measurement, the cat is not alive or dead. It is, in a very real sense, 50% alive and 50% dead at the same time. This scenario is, of course, paradoxical. Cats, as we know them, are decidedly either alive or dead. We never encounter a zombie cat hybrid. The purpose of the experiment was to show the absurdity of applying quantum rules to the large-scale world. And yet, the math holds. The experiment dramatically highlights this bizarre boundary between the fuzzy, probabilistic quantum realm and the solid definite reality we experience every day. Where is that line drawn? What is it about the act of opening the box, of an observer gaining information, that forces nature to make a choice? This leads to an even more radical idea, one championed by the legendary physicist John Wheeler. He coined the phrase, "it from bit." The it refers to all of physical reality, matter, energy, space-time. The bit is the fundamental unit of information, a yes or no answer obtained from a measurement. Wheeler's concept suggests that the physical world at its core might not be made of substance, but of information. Reality, in this view, is forged from the questions we ask of it. The universe becomes real, it becomes concrete, only when it is observed. This is where the journey takes a turn into truly profound and controversial territory. If measurement is what collapses the quantum wave of potential into a single concrete reality, and if we can't define what a measurement is without running into paradoxes like Wigner's friend, then perhaps the chain of measurement must end somewhere definitive. For some of the founding fathers of quantum theory, including the brilliant mathematician John von Neumann and Nobel laureate Eugene Wigner, the only logical place for that chain to end was in the one place that is undeniably non-physical: consciousness itself. This is a breathtakingly radical idea. It proposes that consciousness is not just some accidental byproduct of complex computation in the brain. Instead, it is a fundamental and irreducible component of the universe's machinery. In this view, matter remains in an indefinite state of pure potential, until it interacts with a mind. The electron is just a smear of probability until a conscious observer looks, and that act of conscious observation is what forces it to become a real particle in a real place. The mind, in this framework, is the midwife of reality, delivering the actual from the realm of the possible. Let's be clear, this is a highly controversial and minority view in physics today. But it's a direct philosophical consequence of taking the mathematics of quantum theory at face value. It suggests that a complete description of physical law is impossible without making reference to consciousness. The line between the detached objective world of science and the intimate subjective world of experience completely dissolves. We are not just passive observers of a pre-existing universe. We are, in some fundamental way, co-creators. Imagine reality as a vast, unrendered video game. The code for every possible outcome exists, but the world itself only snaps into high-resolution detail when the player, the conscious agent, turns their attention to it. This isn't just a philosophical game, it's an attempt to solve the deepest paradox in physics by linking it to the deepest mystery in biology. It suggests that the universe may not have a definite reality until a conscious being is there to witness it. But what if the observer, conscious or otherwise, is a red herring? What if the universe doesn't need us to make up its mind? This is the position taken by one of the most brilliant minds in modern physics and mathematics, Sir Roger Penrose. Penrose approached the problem from a completely different direction, starting not with physics, but with the nature of human understanding itself. He argued compellingly that the human mind possesses a quality that no computer, no matter how powerful, can ever replicate: genuine understanding. Specifically, he pointed to mathematical insight. Through Gödel's incompleteness theorems, we know there are mathematical truths that can be recognized as true by a human mathematician, but can never be proven by any formal algorithm or computational system. That aha moment, that flash of insight, Penrose argued, is evidence of a non-computational process happening in the brain. If consciousness transcends computation, he reasoned, then its physical basis cannot be found in the classical, computational physics that governs our everyday world and our digital computers. It must be rooted in the strange, non-computational aspects of the quantum world. But Penrose was deeply unsatisfied with the idea that a conscious observer was needed to collapse the wave function. He felt this was too subjective and mystical. So he proposed a radical new mechanism he called objective reduction, or OR. Penrose suggested that quantum superposition isn't just a mathematical abstraction, it's a real physical state. He imagined that when a particle is in a superposition of being in two places at once, it actually creates two tiny competing curvatures in the fundamental geometry of space-time. Think of it as two tiny, conflicting dimples on the fabric of reality. According to Penrose, this state of having two rival spacetimes is fundamentally unstable. It can only last for so long. When the separation between these spacetime curvatures reaches a critical, objective threshold, the system collapses on its own, without any need for an observer or a measurement. The choice of the final state, in Penrose's model, is neither random, as in standard quantum mechanics, nor determined by an algorithm. Instead, he believes it is influenced by information encoded in the very fabric of the universe at the tiniest possible level, the Planck scale. In this model, collapse is a real physical process governed by the laws of quantum gravity. It's a feature of the universe itself, a moment where a choice is made, and this choice, he would come to argue, is a moment of proto-consciousness. Penrose's theory was elegant physics, but it was missing a crucial piece, a home. Where in the warm, wet, chaotic environment of the brain could such a delicate quantum process possibly take place? A new theory of physics needs a biological partner. That partner came from an unexpected field. Anesthesiology. Dr. Stuart Hameroff, an anesthesiologist, had spent his career studying the very nature of consciousness by exploring how, precisely, anesthetic molecules turn it off. He was convinced that the standard neuroscientific answer, that anesthetics simply disrupt communication between neurons at the synapses, was incomplete. The real action, he believed, had to be happening at a much deeper, subcellular level. When Hameroff read Penrose's work, he had his own aha moment. He realized that Penrose's abstract physical theory of objective reduction might have its biological stage inside the very structures he had been studying, the microtubules within our neurons. This collaboration between the mathematical physicist and the anesthesiologist gave birth to one of the most detailed, ambitious, and controversial theories of consciousness ever proposed: the orchestrated objective reduction theory, or Orch OR. Here's the essence of the theory. Orch OR proposes that the non-computational quantum processes Penrose described are the physical basis for consciousness, and they occur within the microtubules. According to their model, quantum computations, specifically superpositions of oscillating protein subunits within the microtubules, evolve over time. This quantum computation is orchestrated by the brain's biological processes, shielded from the noisy environment. The superposition continues to grow and involve more and more of these subunits until it reaches the critical threshold for Penrose's objective reduction. At that moment, the system collapses on its own. And this physical event, this self-collapse of the quantum state, is a moment of conscious awareness, a flash of experience. Our seamless stream of consciousness, in this view, is actually a sequence of these discrete moments of collapse, like frames in a movie, happening at frequencies up to millions of times per second. Orch OR, therefore, makes a bold and specific claim. It links the deepest level of reality, the geometry of space-time, directly to the inner world of the mind, via the quantum architecture of the brain. To understand the Orch OR theory, we have to zoom in, way past the neuron itself, and into its very skeleton. This is where we find the microtubules. For a long time, these tiny, hollow, cylindrical protein assemblies were seen as little more than cellular scaffolding, the girders and beams that give the neuron its structure and act as highways for transporting molecules. But Stuart Hameroff saw something more. He proposed they were the perfect candidates to be the brain's quantum computers. Why? First, their structure. Microtubules are built from small, peanut-shaped proteins called tubulin. These tubulin proteins are arranged in a highly ordered crystalline lattice, almost like a biological semiconductor. This precise, repeating structure is crucial, as it could allow delicate quantum effects to propagate collectively. Second, inside these tubulin proteins are small pockets that are hydrophobic, meaning they repel water. These pockets could create an isolated, non-polar environment, effectively shielding delicate quantum states from the noisy thermal chaos of the rest of the cell, like a tiny insulated quantum sanctuary. Hameroff proposed that electrons within these pockets could enter into a state of quantum superposition, and through their collective organization, these tiny superpositions could link up and spread along the microtubule. But is there any evidence for this? The idea seemed highly speculative for years, until the groundbreaking experimental work of researchers like Dr. Anirban Bandyopadhyay. His lab at the National Institute for Materials Science in Japan discovered that microtubules exhibit surprisingly high-frequency electrical oscillations in the megahertz and gigahertz range. This suggests they are acting as subcellular information processors, operating at speeds far beyond the slow, classical firing of neurons. Bandyopadhyay's team has even provided evidence for quantum vibrations and coherence in microtubules at warm temperatures, a finding that lends significant, though not definitive, support to the idea that these structures are not just the brain's skeleton, but its quantum scaffolding. For a very long time, the biggest objection to any theory of quantum consciousness was simple. The brain is too warm, wet, and noisy. Quantum effects like superposition are notoriously fragile. In the lab, quantum computers have to be cooled to near absolute zero and shielded from the slightest vibration to prevent a phenomenon called decoherence, where the quantum state collapses due to interaction with the environment. Surely any quantum coherence in the brain would be destroyed in less than a nanosecond, far too quickly to be useful for neural processing. This was a powerful and seemingly fatal criticism. However, in the last couple of decades, a revolutionary new field has emerged that turns this objection on its head: quantum biology. Scientists are discovering that nature isn't just aware of quantum mechanics. It has evolved to master it. Life, it turns out, operates on the quantum edge. The most stunning example is photosynthesis. When a photon of light hits a chlorophyll molecule in a plant leaf, its energy needs to be transported to a reaction center to be converted into chemical energy. Classically, this energy would bounce around randomly, trying to find the most efficient path, and much of it would be lost as heat. But what actually happens is that the energy enters a state of quantum coherence, allowing it to explore all possible paths simultaneously and instantly find the most efficient route. This process is nearly 100% efficient, a feat that would be impossible under classical physics. And it's not just plants. The uncanny ability of migratory birds like the European robin to navigate thousands of miles using the Earth's magnetic field is now best explained by a quantum mechanism. It's believed that a protein in the bird's eye called cryptochrome contains electrons that become quantumly entangled. The Earth's weak magnetic field influences how these entangled electrons behave, creating a chemical signal that essentially allows the bird to see the magnetic field lines as a pattern superimposed on its normal vision. These discoveries are profound. They prove that life has evolved sophisticated tricks to protect and exploit fragile quantum effects in warm, wet, and noisy biological environments. If a plant can do it for energy and a bird can do it for navigation, the idea that the brain might do the same for a function as sophisticated and mysterious as consciousness suddenly seems far less radical and far more plausible. Despite its elegance and the supporting evidence from quantum biology, the quantum consciousness hypothesis, particularly Orch OR, is far from universally accepted. In fact, it remains on the fringes of mainstream science and faces a barrage of powerful criticisms. The most persistent and damaging attack is the problem of decoherence. Physicist Max Tegmark famously performed a calculation which concluded that any quantum coherence among tubulins in the brain's warm environment would be destroyed by decoherence in mere femtoseconds. That's a millionth of a billionth of a second. This is many, many orders of magnitude too fast to influence the much slower processes of neural firing, which happen on the millisecond timescale. While Hameroff and Penrose have countered that microtubules might have unique properties to shield coherence, Tegmark's calculation remains a major hurdle for the theory. Most neuroscientists, for their part, simply believe that quantum mechanics is an unnecessary complication. They argue that classical models based on the interactions of large-scale neural networks are doing an increasingly fantastic job of explaining brain function. They point to the successes of computational neuroscience in modeling perception, learning, and decision-making, and argue that consciousness is simply an emergent property of this incredibly complex classical network. Why, they ask, do we need to invoke the ghost of quantum physics when the classical machine is already so capable? Meanwhile, within the physics community, many argue that the entire premise is built on a misunderstanding of the measurement problem. There are other interpretations of quantum mechanics that resolve the paradox without ever needing to invoke a conscious observer or a special collapse mechanism like Penrose's. The most famous of these is the many worlds interpretation, which posits that the wave function never collapses at all. Instead, at every quantum measurement, the universe itself splits into multiple branches. In the case of Schrödinger's cat, the universe divides into one reality where the cat is alive and another, equally real, parallel universe where the cat is dead. In this view, there is no paradox to solve and no special role for consciousness. It is just a phenomenon that exists within each of these branching realities. While the quantum debate rages on, a powerful and influential alternative has emerged that takes a completely different approach. It's called Integrated Information Theory, or IIT, and it was developed by the neuroscientist and psychiatrist Giulio Tononi. Unlike the quantum theories, which start with the strange laws of physics and try to build a bridge to the mind, IIT starts with the mind itself. It begins not with physics, but with phenomenology, the undeniable properties of our own conscious experience. Tononi starts by identifying 5 essential properties, or axioms, of any conscious experience. It exists intrinsically, for itself. It is structured, composed of many elements. It is specific. It is what it is, and not something else. It is unified. It's a single whole experience. And it is definite. It has boundaries. From these axioms, he derives a set of postulates about what kind of physical system could possibly support such an experience. The key idea is that consciousness is identical to a system's capacity to integrate information. He gives this capacity a mathematical value, which he calls phi, f. A system is conscious, according to IIT, to the degree that its whole is more than the sum of its parts. To put it another way, a system has a high phi value if it has a large repertoire of possible states. It's highly differentiated. And if its components are so deeply interconnected that you cannot break the system down into independent parts without a massive loss of information, it's highly integrated. A digital camera sensor has millions of photodiodes, each with information, but it has 0 phi because the pixels are not integrated. They don't talk to each other. The camera's processor, which integrates that information to form an image, has some phi. The human brain, with its massive and intricate network of feedback loops, has an extraordinarily high value of phi. In this view, consciousness isn't an all-or-nothing quantum event. It is a fundamental property of any system with a sufficiently high phi, making it a graded, measurable feature of reality. IIT predicts that anything from a simple thermostat to the internet could have a small amount of consciousness, a view that flirts with a much older philosophical idea. There is another related idea that often gets confused with theories like Orch OR, but is actually quite distinct. This idea doesn't necessarily claim that consciousness causes quantum collapse, but rather explores whether the brain functions not just as a classical computer, but as a quantum computer. This is a question of processing power. A classical computer bit is always in a definite state, either a 0 or a 1. A quantum bit, or qubit, however, can exist in a superposition of both 0 and 1 at the same time. This ability to explore multiple possibilities at once allows quantum computers to perform certain calculations exponentially faster than any classical computer ever could. Proponents of the quantum brain hypothesis argue that the sheer power and efficiency of the human mind, our ability for rapid intuition, for complex pattern recognition, for the creative leaps that lead to scientific discovery or artistic genius, might be explained by quantum algorithms operating at the molecular level. Perhaps when you are faced with a complex decision with dozens of variables, your brain doesn't weigh each option one by one, like a classical computer. Instead, perhaps it enters a quantum state where all potential options are explored simultaneously in superposition. The gut feeling, or flash of insight, that follows could be the result of this quantum computation collapsing into an optimal solution. In this framework, consciousness isn't necessarily the magical ingredient that collapses the wave function for the universe. Rather, consciousness itself might be an emergent property of the uniquely powerful type of information processing that only a biological quantum computer could achieve. The brain may have evolved to harness the strange logic of the quantum world not to create reality, but simply to think better and faster. While this idea still faces the same daunting decoherence problem, it separates the mechanics of brain function from the grander, more metaphysical questions of reality, offering a slightly more grounded, though still highly speculative, path for inquiry. For any of these fascinating ideas to move from the realm of philosophical speculation into the world of accepted science, they need one thing: hard, empirical evidence. And that is the monumental challenge facing the field of quantum consciousness. How do you test for a quantum process happening deep inside the brain, a process that might be the very source of the person doing the testing? It's a daunting task, but researchers are beginning to pursue several clever experimental avenues. The team led by physicist Anirban Bandyopadhyay continues their work probing the high-frequency electrical resonances of individual microtubules. By zapping them with electromagnetic fields and listening for the frequencies at which they vibrate, they are searching for signatures that can only be explained by quantum mechanics. It's like trying to hear a quantum hum beneath the loud classical noise of cellular activity. Each new finding that demonstrates quantum effects in these structures at biological temperatures adds another piece to the puzzle, bolstering the physical plausibility of the theory. Another, and perhaps more powerful line of attack involves anesthetics. This is the cornerstone of Stuart Hameroff's contribution and a key prediction of the Orch OR theory. The theory makes a very specific, testable claim. General anesthetics don't just work by gumming up the synapses between neurons. They produce unconsciousness by binding directly to the tubulin proteins within microtubules and dampening their quantum vibrations. If researchers can show a clear correlation, that the potency of different anesthetic molecules is directly related to their ability to suppress these specific quantum oscillations, it would provide a powerful and direct link between a subcellular quantum event and our conscious experience. These experiments are still in their early stages, but they represent a critical shift. The hunt for evidence is on, moving the quantum mind from pure theory to a testable scientific hypothesis. The power of anesthesia as a scientific tool cannot be overstated. It gives us a unique ability, a reliable, reversible switch for human consciousness. Every day, all over the world, we turn people's consciousness off, and then, a few hours later, we turn it back on. Understanding precisely what that switch is and how it works could reveal the fundamental mechanism of awareness itself. The traditional view in neuroscience is that anesthetics work on a broad, network level. They are thought to bind to receptor proteins on the surface of neurons, primarily at the synapse, either by suppressing excitatory signals or enhancing inhibitory ones. Essentially, they quiet the chatter between neurons until the large-scale network activity required for consciousness breaks down. The quantum hypothesis, however, suggests a far more specific and deeper action. According to Orch OR, anesthetic molecules, which are nonpolar and interact via weak quantum-level attractions called van der Waals forces, are perfectly suited to get into the hydrophobic pockets within the tubulin proteins. Once there, they interfere directly with the delicate electron clouds responsible for the quantum coherence. They don't just quiet the neurons, they stop the quantum music within them. This provides a clear, testable distinction between the two models. Recent experiments have provided tantalizing support for the quantum view. For instance, a 2024 study showed that giving rats a drug that specifically stabilizes microtubules made it take significantly longer for them to be knocked out by an anesthetic gas. The microtubule stabilizing drug appeared to interfere with the anesthetic's action, supporting the idea that the anesthetic needs to act on microtubules to cause unconsciousness. Another study found evidence that anesthetic drugs do indeed reduce the duration of quantum excitations within microtubules. By studying precisely how different anesthetics dampen these quantum effects and how that correlates with the loss of awareness, researchers hope to finally find the physical light switch for consciousness, and in doing so determine if its true location is in the classical network or the quantum heart of the cell. As we grapple with the sheer difficulty of explaining how consciousness could spring into existence from seemingly mindless matter, some philosophers and scientists are reviving one of the oldest and most mind-bending ideas in human thought: panpsychism. This is the view that consciousness isn't a special, emergent property that only appears in complex brains. Instead, panpsychism proposes that consciousness, in some rudimentary form, is a fundamental and ubiquitous feature of the physical world itself. In this framework, an electron, a quark, or a photon isn't just a dead fleck of matter. It possesses a primitive, simple form of experience, a kind of proto-consciousness. This isn't to say that an electron feels anxiety or a rock contemplates philosophy. The claim is far more subtle, that there is something it is like to be an electron, however simple and unimaginable that experience might be. The incredibly rich and complex consciousness of a human brain, in this view, doesn't arise from creating awareness out of inert, non-conscious stuff. That, the panpsychist argues, is a magical leap that can never be explained. Instead, our consciousness is a result of organizing and combining these countless points of fundamental, simple experience into a vastly complex and unified whole. Panpsychism elegantly dissolves the hard problem by claiming it was a misconception from the start. The problem was never, how do you get mind from matter, because matter was never truly mindless to begin with. While it may sound strange, this view has been considered by thinkers from Plato to William James and Bertrand Russell, and is now being taken seriously again by contemporary philosophers like David Chalmers, and physicists who see it as a potential way to integrate experience into our physical theories from the ground up. It paints a picture of a universe that is not a cold, dead machine with a few accidental sparks of awareness, but a cosmos that is saturated with experience at its very core. The enduring mystery of consciousness might not just be a problem for biologists and philosophers, it could be the critical missing piece in physics itself. For the past century, physics has been dominated by two incredibly successful but mutually incompatible theories: general relativity, which describes the large-scale universe of gravity stars and galaxies, and quantum mechanics, which describes the small-scale world of atoms and particles. The holy grail of modern physics is to unify these two into a single, elegant theory of everything. But after decades of effort, this unification remains elusive. Some of the most visionary physicists have speculated that the roadblock is our exclusion of the observer from the equations. We treat the universe as an objective thing that we are merely looking at. But what if that is the fundamental mistake? The physicist John Wheeler, who coined the terms black hole and wormhole, proposed a concept he called the participatory universe. In this view, reality is not a fixed, pre-existing state. It is a dynamic process that is brought into being through acts of observation. He famously drew a diagram of the universe as a giant U, with the beginning of time on one arm, and an observer, us, on the other, looking back. The arrow of observation, he suggested, goes backward in time, and the observations we make now play a role in creating the reality of the deep past. In such a universe, consciousness cannot be an afterthought, a random development on a single tiny planet. It must be a central and fundamental component of the cosmos. A complete theory of the universe from this perspective would not just describe the interactions of matter and energy, but would have to include the rules that govern the interaction between matter and mind. The next great revolution in physics, therefore, may not come from building bigger particle colliders, but from a radical unification of the objective laws of the cosmos with the subjective reality of the observer. To truly understand the universe, we may first have to understand ourselves as an integral part of it, the part through which the universe itself becomes aware. Our journey has taken us from the firing of a single neuron to the very fabric of space-time, from the classical machine to the quantum ghost, and from the inner world of the mind to the outer limits of the cosmos. And yet the central question, is consciousness a quantum mystery, remains tantalizingly unanswered. What has become clear is that the old, simple explanations are no longer enough. The classical model of the brain as a complex computer, for all its power, still cannot account for the simple, undeniable fact of our own experience. It describes the machinery, but it cannot find the ghost within. Quantum theories, like the ambitious Orch OR model, offer a breathtaking alternative. They provide a potential, though unproven, bridge between the profound strangeness of the quantum world and the profound mystery of the inner world. They hint at a reality where our minds are not separate from the physical universe, but woven from its deepest, most fundamental threads. Alternative frameworks like integrated information theory challenge us to rethink what information is and suggest that consciousness is a spectrum, a measurable property of reality itself. And ancient ideas like panpsychism ask us to consider the most radical possibility of all, that the universe has been conscious in some form all along. The quest to understand consciousness is more than just a scientific puzzle. It forces a convergence of physics, neuroscience, computer science, and philosophy. It pushes science to its absolute limits, forcing us to confront the nature of reality, the role of the observer, and our ultimate place in the cosmos. Perhaps the most profound lesson from this journey is this: the act of asking the question is what matters most. In our relentless pursuit to understand the nature of our own awareness, we find ourselves holding up a mirror to the universe. And in that reflection, we begin to see the possibility that we are not just an accident of biology, but the very means by which the cosmos has evolved to observe and understand itself. The mystery endures, but the search continues, and what we discover along the way will undoubtedly change not just our science, but our very definition of what it means to be human. So what do you think? After hearing these incredible, mind-bending theories, where does your intuition lie? Is consciousness a grand illusion created by a meat computer? Is it a quantum symphony playing out in the architecture of our cells? Or is it a fundamental whisper of the universe itself? I'd love to hear your thoughts in the comments below. Thank you so much for joining me on this journey into the deepest of mysteries. I wish you all the very best of health, and a life full of curiosity and wonder. And if you enjoyed this exploration and want to dive deep into more of science's biggest questions, please consider liking this video and subscribing to the channel. It really helps us continue to create content like this. Until next time,